Hi, everybody. Welcome back to Asymptotics and Perturbation Methods. Today, we'll be talking about something that is a little bit out of the mainstream, which is application of perturbation theory to difference equations, as opposed to differential equations. So in difference equations, either time or space is discrete rather than continuous. These kinds of equations do come up in subjects where time naturally is measured in units of integers, like in economics, sometimes people worry about what's happening this year versus next year, or in population biology, they'll talk about what happens from one generation to the next in the populations. Also, if you do any discrete math, combinatorics, let's say, difference equations come up a lot in the form of recursion formulas. They often get solved using generating functions. Probability and statistics uses them a lot. In dynamical systems, we have the concept of iterated maps. So, these things do come up, but the laws of the universe are written in differential equations rather than difference equations. So as a person who really cares about science of, like a more physical bent, I tend to know more about differential equations than difference equations, but as they say, your mileage may vary. So I was requested to do some examples about difference equations, and so here I am making my best attempt at it. All right, so let's start with the lecture. Okay, here we go. So this is a pretty big subject. I mean, we could spend a whole course on this or more. That is, especially asymptotics of solutions to difference equations is a pretty rich topic. But since we've been talking about the method of multiple scales, I thought I would try to tie difference equations to our recent work on multiple scales. I thought that might be interesting. And so that's the example I want to do today. So as I just said, these arise when we're thinking about discrete time or space. But so the example I want to do is this one, where I've got a small parameter epsilon in the problem right here. It's an equation that has discrete, indices here, n plus 1 and n minus 1. You'll recognize this operator over here acting on y as a discrete version of the second difference, the second derivative. Right? This is a discrete Laplacian, you might say it that way. So this comes up in lots of systems that have second derivatives if it were continuous time. And if we discretize them, then you'll see this type of thing. Over here, I've got a y and also a nonlinear term with a small epsilon in front of it. So an epsilon y cubed. And the reason we're looking at this is because it seems kind of naturally connected to things we did recently. That is, you could regard this as a discretization of Duffing's equation that we talked about a few lectures ago. You may remember when I first introduced the method of multiple scales, we were talking about something called Lindstedt's method, Poincaré-Lindstedt. And so at that time, we did look at this Duffing equation, u double dot plus u plus epsilon u cubed is 0. That was a nonlinear oscillator with a spring that got stiffer or could also soften depending on the sign of epsilon as we stretch the spring. So to see, what do I mean? Why do I say that this could be viewed as a discretization of Duffing's equation? Think of it this way, that suppose I represent time in discrete time steps of delta t. So n delta t, I'm clicking along in time, as would occur if you were numerically solving a differential equation with finite difference methods. So if I write time as n delta t, and then I sample my function u at those discrete times, so u at the time of interest is u of n delta t. That's what I'm considering as my yn. in these equations up here. So now, what does that have to do with Duffing's equation? So let me now write down what is the discrete counterpart of a first derivative or a second derivative, just in case this is not familiar to you. So for instance, a first derivative, u dot. At the lowest order of approximation, you could think of it as, u at time t plus delta t minus u at t divided by delta t, right? That's the difference quotient that appears in the definition of the derivative if we took the limit as delta t goes to 0. But suppose we don't take delta t going to 0. We're just keeping some finite, non-zero time step. Then this would only be approximately true for small delta t. And, if we write that in terms of our notation, this would be u at n plus 1 times delta t minus u at n delta t all over delta t. And so in terms of this quantity y that I've defined, this is just y n plus 1 minus yn all over delta t. Okay, so that's how you would write first derivatives in this discrete way. And then similarly, a second derivative well, that would give me, by the same kind of reasoning, u double dot would be approximately yn plus 1 minus yn over delta t. That's a u dot, approximately at one time step, minus itself, well, minus the one at the previous time step. So yn minus 1 all over delta t. So that's a difference in the y dots. Those are u dots. And then that difference, to make a difference quotient, has to be divided by delta t. So that gets me a discrete second derivative. And if you put all that together, then you get that this is yn plus 1 minus 2yn plus yn minus 1 all over delta t squared. Okay, so that's the kind of thing you'd be used to if you've ever taken a numerical analysis course. You'd see these kind of moves made all the time. Anyway, so when I put all that together, put that into Duffing's equation. So the discrete version of u double dot plus u plus epsilon u cubed equals 0. The discrete analog of that would be y n plus 1 minus 2yn plus yn minus 1 all over delta t squared. So that's my second derivative. Then plus u, I'm calling that yn. And plus epsilon u cubed, that'd be analogous to epsilon yn cubed. All of that is 0. And if you rewrite that suitably, well, I mean, this equation, I mean, compare that with what I have way up here at the beginning, this one. You see that they're the same thing, except that this quantity minus 2 omega squared, the role of that is being played by, if I multiply across by this delta t squared, put it in here. So in other words, what I'm saying is my 2 omega squared is delta t squared. But where delta t squared is 2 omega squared. So that's the translation. Whoops. And you might wonder, why do I have that factor of, oops, sorry, I need squared. Oh, crumbs. Me and my fastidiousness with these boxes. Excuse me. Get up there, you demon. There. What's that 2 doing there? Well, that's in the same spirit of fastidiousness. You're going to need the 2 at some point in the calculation, it turns out. And so by inserting it now, I save myself a lot of 2's later on. You'll see that it's just convenient to have the 2 there at this stage. It's not very important. The 2 saves many 2's later on. Okay, so anyway, that was just to make the case that this equation is sort of a discrete version of Duffing's equation. Now, if you remember what happened with Duffing's equation, when we had a small epsilon, it's basically a small perturbation of a simple harmonic oscillator. And the one thing that was different, though, is that its frequency didn't stay, at the unperturbed frequency. It got a frequency shift due to the stiffening of the spring. And so we would expect a frequency shift with sinusoidal behavior in this discrete context also. And we're going to see that's actually going to happen. So so by analogy, with the Duffing equation, so we would expect the solutions for yn to be nearly sinusoidal with a frequency that depends on their amplitude. I mean, hopefully you remember that with the Duffing equation, that when it oscillates at larger amplitude, you're sort of sampling more places where the spring is stiff. And so that's going to raise the frequency in a way that depends on the amplitude. So anyway, we saw all that, and we're going to see it again. So just as a reminder, earlier we solved that Duffing problem for the periodic orbits using the Poincaré-Lindstedt method. Whereas what we're doing now is the method of multiple scales, which is really a superior version of Poincaré-Lindstedt that also lets you deal with transient behavior and stability. So now multiple scales will work. But here we'll use specifically 2 timing. Okay, so let me start diving into the analysis. Do you want to ask anything at this point?
Do we care how large omega is?
Yeah.
I ask because for the discrete approximations of the derivative to be any good, we would want delta t to be fairly small.
That's right.
So should we be thinking of omega itself as very small?
That's a good question. Yeah, that's a good question. So to the extent that omega is very small, the system should be more faithfully captured by the Duffing behavior. And so, yeah, that's a good point. You might expect something funny to start happening when omega gets bigger. Certainly that's the rule of thumb, right? I mean, if you take like something called the logistic differential equation and discretize it, then you get the logistic map. And they have really different behavior because the logistic map is sort of like solving the logistic equation with a delta t of 1. And then you can have chaos, whereas the logistic differential equation can't do anything interesting. It only has, monotonic convergence to a fixed point. So that's a good bit of intuition. Yes. Did I not say anything about the size of omega? I mean, I did say
it
up
was
here,
less than 1.
yeah, less than 1. But yeah, you might expect something funky to start happening as omega gets sufficiently large. Let's see. Yeah, I didn't really investigate that, so I'm not playing possum with you here. I don't actually really know if anything funny happens as omega gets large. You might expect it. So yeah, let's see. But other questions about this? Okay. So all right, let's see. We're going to do the method of 2 timescales. So we already have 1 timescale, which is, integers, n is clicking along in steps of 1. So 1 is the short time scale or something. And I'm going to or n, I don't know how you want to say it. Let's let our slow time scale be s. That'll be epsilon n. So this is analogous to the usual tau equals epsilon t. Sorry, sort of like tau equals epsilon t in the continuous case. Okay, so there's my slow time. And I'm going to assume a form for the solutions, which will be that yn will be asymptotic to y0 n comma s plus an epsilon y1 n comma s plus etc. Right, so we have variations on both the fast time, which is going to be these sinusoidal oscillations, and then slow time, maybe some evolution of the amplitude or phase of the oscillation. Okay, so I have all that for my ansatz for yn, and now, because I'm dealing with a differential a difference equation, I have to rewrite terms like, see, these have different subscripts. I have to write what is now yn minus 1 or yn plus 1 in terms of this. So that requires a little concentrating. I mean, this is analogous to transforming derivatives. So then, let's see, to lowest order, you might remember that when you transform derivatives in the method of 2 timescales, you get 2 terms, right? There's one from the fast time and one from the slow time. So it's a little tricky. So let's see how that plays out. If we do yn plus 1, actually, let's do both cases at the same time. We'll do yn plus or minus 1. What's that going to be? Well, so certainly, I could just copy and say that's going to be y0 and plus or minus 1s plus epsilon y1 and plus or minus 1s. Now, you might be wondering, wait a second, why isn't the s being shifted? Good question. It probably should be, right? Maybe, okay, let's do that. Should be, actually. right? S is getting shifted by, because after all, S is linked to n by epsilon n. So really this should be S plus or minus epsilon. Yeah, getting in trouble there. See, I'm not used to this kind of stuff. And then this better be S plus or minus epsilon. Just to be careful here. Now, what we want is to compare that to what's happening at time. I don't want the S to be changing. It'd be good if, on the slow times, when things are happening on the fast time scale, it's almost like they're not changing at all on the slow time scale. So, this is sort of incorporating the idea that we want to treat S and N as independently as possible. So I'm going to look for an approximation here, which is, I want to think of this as y0 at n plus or minus 1 comma s. Notice not s plus or minus epsilon, but then make appropriate corrections to that coming from the formula above. So I claim there are two corrections. One of them is just sort of what you get from this term. If we ignore the fact that S has advanced or changed to S plus or minus epsilon, if we just replace it by S, that will incur an order epsilon error. Sorry, an order epsilon error due to this. And that order epsilon will multiply this order epsilon to make an order epsilon squared that's going to get put into this garbage pile of ... that we're not dealing with. At the same order, I can just replace this term by epsilon y1, and minus 1 comma s at the cost of this squared error that I'm not going to worry about. But I also have another term, which is, so maybe I should say plus order epsilon squared. But then there's also, oh, did I get frozen there for a second? It said my internet was unstable. Sorry, no, hope not. Okay, then there's also the issue of if I did allow S to vary, up here in this order 1 term, right? This whole thing is order 1. So taking account of the fact that S is varying by epsilon, that will produce an order epsilon correction that is comparable in size to this stuff, that is going to be generating a term that looks like this. It's actually going to be plus or minus because it depends on if I take which of these plus or minus signs right there. So I'm going to get a plus or minus partial with respect to S of y0 evaluated at this point, n plus or minus 1 comma s. Sorry, I forgot the 1. So, I mean, if you don't want to think too hard, you could just sort of do multivariable Taylor expansion and keep the order epsilon term, where you're expanding around the point n plus or minus 1 comma s. If you just wrote down the multivariable Taylor series for this to order epsilon, you would get the two terms I just wrote down, where we're consistently using this as our reference point to expand around. And I need an epsilon in front of this. That was the whole point here. So I think I've done that right. And then plus, again, there's an order epsilon squared error. So are you with me with that? To transform those derivatives? Yeah, or not derivatives, but those discrete differences. Okay, so if you accept all that, then I'm going to substitute that stuff into the difference equation. So we'll get, so by the difference equation, I'm referring to this. This is my difference equation. Okay, so I'm going to substitute for the yn plus 1 and the yn minus 1 in there. And I don't want to write out the whole mess. I'm going to get a bunch of stuff, right? Because I have order 1 terms here. I have order epsilon term here and here. And I also had, back in this equation, well, I have an order epsilon term here, and I have various order 1 terms. So when you collect all the stuff that's order 1, here's what you get. Okay, at order 1, we'll get y0 n plus 1 comma s minus 2y0 ns plus y0 n minus 1 s. So it's coming from my discrete Laplacian operator. And all that is going to equal minus 2 omega squared y0, running out of room. Let me move all this to the left. Y0 ns. Remember, this omega squared is just a constant that's coming along for the ride that depends on our step size. You may be wondering, like in Poincaré-Lindstedt, we had to adjust the frequency. Somehow that's going to be dealt with here. You'll see how. There's going to be a phase term that's going to enter our solutions, and that phase will have a discrete derivative that's going to relate to the changed frequency. So this will happen, but it's not, we're not building it in. We're just doing multiple scales at this point. So anyway, there's order 1. Now it's a lot of notation with all these double arguments. So I'm going to ease the notation a little bit by letting a sub n equal y0 n comma s. I'm just going to work with that a sub n for a while. So in those terms, my lowest order equation here at order 1 is just an plus 1 minus 2. Actually, notice here I've got a 2 times a y0, and here's a 2 omega squared times a y0. That's one place where this 2 is coming in handy that I inserted earlier. So it's just going to factor into 2 times 1 omega squared a sub n plus a sub n minus 1. All of that equals 0. That's my governing equation at order 1. And that's a linear difference equation. It's actually a second order linear difference equation, as you can see, because the indices differ by 2 between n plus 1 and n minus 1. So it's interesting. I mean, we're getting a linear equation, just like when we do perturbation theory, we get linear differential equations at each order. We're getting now a linear difference equation at this first order. And you're supposed to know how to solve linear difference equations with constant coefficients, just like you're supposed to know how to solve linear differential equations with constant coefficients. But since these aren't so familiar to many of us, let me just walk through that. So what would we say? By analogy with differential equations, you should look for exponentially growing or decaying solutions, right? In continuous time, you always plug in e to the RT or e to the lambda t. So the analog of that, since t is like n, and you could think of it this way, right? Sort of, this is very loose, but like e to the RT is the usual move. That kind of is like e to the R to the t. And t is sort of like n. So it's sort of like something to the nth power. And so the correct move is guess, in the method of undetermined coefficients, you want to guess that a sub n is just something raised to the nth power, where this lambda plays the role of e to the r. The e isn't doing anything for us. I mean, e to the r is just some number. So we might as well call it lambda. And so that turns out to be how you solve difference equations with constant coefficients if they're linear. Just guess lambda to the n. You may already know that if you've taught, like maybe you guys are teaching assistants in a linear algebra course. And a good use of linear algebra is to solve linear difference equations with constant coefficients. You could solve it with eigenvectors and matrices and that kind of thing. So anyway, if I guess an, I don't even know what symbols to put in here. It's sort of so sloppy what I wrote. I sort of want to put like 3 wiggly equal signs to, I almost feel like just erasing that whole thing. Maybe I'll just, since I'm so embarrassed by it, I'm going to make it really small and cockeyed and put it off here to the side. Okay. But that's sort of my motivation for the guess. All right, so if you make that guess, then what happens in the difference equation? You'll get lambda to the n plus 1 minus 2, 1 minus omega squared, lambda to the n plus lambda to the n minus 1 equals 0. And now you can cancel out a lot of lambdas, whole lambda to the n minus 1 worth of them. And so then this becomes lambda squared minus 2, 1 minus omega squared lambda plus 1 equals 0. And that's a quadratic equation. So we can solve that. Actually, it's convenient to introduce another letter. Let me let b equal 1 minus omega squared. So I don't have to drag around all those symbols. So this is lambda squared minus 2b lambda plus 1 equals 0. And then from the quadratic equation, that gives us lambda equals 2b plus or minus the square root 4b squared minus 4 all over 2. And so now again, you see why the 2's are so convenient to have introduced earlier. They all cancel out. You get a 2 coming out of the square root because of those 4's in there. So it's b plus or minus. Actually, maybe I should say something. Hold on 1 second here. With this choice of notation for b, remember omega squared was less than 1, between 0 and 1. So this b is greater than 0, isn't it? But it's less than 1. Yeah.
You said so in the beginning.
I said omega was between 0 and 1. So b is also going to be between 0 and 1. And that means that b squared minus 1 is going to be strictly negative inside that square root. So what I have is plus or minus I times the square root of 1 minus b squared. Where that quantity inside the square root is positive. And then and actually the 2's have canceled out. So that's actually a very pretty expression. In fact, you can see from that expression that lambda is of modulus 1 as a complex number. Because, like if you draw it on the circle in the complex plane, you'd have, let's see here. Let's see if I can pull off drawing a circle in Notability here. Not bad. Okay, that's pretty good. Right, so this is like, this is the real lambda axis. Here's the imaginary lambda axis. Alpha you can think of as, so this is a unit circle. Here I'm drawing, this distance is b. This is a unit circle, that's a 1. And this vertical distance is square root of 1 minus b squared. So I'm just trying to make the point that lambda lives on the unit circle. And that's interesting. So we can say here, if I call alpha this angle inside the circle, then my lambda is of the form e to the I alpha. Actually, yeah, okay, I'll say it like that. I have in my notes plus or minus e to the plus or minus I alpha. I'm confused. Why would I write that? Oh, I see. Because I'm thinking, right, that's because I have these two cases. Plus or minus I, that times that square root. So right, so actually there's two different lambdas. Good point. So I better say, there's two, right, of course, there's two roots for lambda. So I get plus or minus I alpha. Yeah. Where the alpha satisfies cosine of alpha is b over 1, which is just b, which in terms of my omega was 1 minus omega squared. So let's record that for posterity. You might need that later. Okay, and we'll use this too. All right, so in terms of all that stuff, what was the point of all that? I had to solve this linear difference equation, and I've just solved it. I just got two linearly independent solutions. There are these two different lambdas to the nth power. So my general solution so the general solution to the order 1 difference equation is A1, or AN, sorry, A sub n, is some constant, let's say C1 lambda 1 to the nth power plus some other constant C2 lambda 2 to the nth power. And plugging in those two lambdas, this is giving us C1 e to the I alpha n plus C2 e to the minus I alpha n. And that's starting to look pretty sinusoidal, right? That's what we were hoping would happen by analogy with Duffing's equation. In fact, we could even write it as explicitly as a cosine, as in terms of some other constant, let's call it capital A. Cosine of alpha n plus a phase angle that I'll call theta, where the A and the theta are related to those complex constants C1 and C2 in some way that not interesting to figure out. The point is, AN is actually sinusoidal, or if you prefer, cosinusoidal. But the interesting thing is that these, the A and the theta, keep in mind, we've been solving the problem in terms of the fast time scale n. These constants are not really constants. They're constants on the fast time scale, but really what they are is functions of the slow time s, just as in any multiple scale calculation. So a is really a function of the slow time s, and so is theta. So we're seeing something that's basically a sinusoidal oscillation with a slowly modulated amplitude and phase, just like we would expect, except this is now the discrete counterpart. Okay, so that's a good natural place to pause. You want to ask anything at this stage? All right, so let me just summarize that then. Summary so far, that y0, our lowest order solution, n comma s, is asymptotic to something of the form a of s cosine alpha n plus theta s, where we had this quantity alpha introduced in such a way that cosine of alpha is related to the original step size, or the parameter omega, by cosine alpha equals 1 minus omega squared. Okay, so that's what we have so far. All right, now let me put in a big barrier because that was sort of the end of the order 1 stuff. Okay. Next, let's go to order epsilon. Because we know that at order epsilon, we'll be getting the amplitude equations, right? These will be the things which, by getting rid of secular terms, will tell us how the amplitude and the phase theta, how those behave on the long time scale. So we expect that to take place again. All right, so I have order epsilon equations that come from way back where? I mean, what? This is stuff I didn't write down. It was, I had to take all these first differences and plug them into the original difference equation, and then I'd have to collect order 1 and order epsilon terms. I didn't write it all out, but if you collect the order epsilon terms, here's what you would get at this stage. You'll get y1 n plus 1s minus 2. I'm tempted to write b again, but in my notes I have 1 minus omega squared. y1 n comma s plus y1 n comma s. So notice this is a linear difference operator acting on this function y1. This is, I'm just sort of underscoring what we've said many times in this course, that this is the same linear operator that we saw seen at the order 1 problem. It's that sort of simple harmonic oscillator looking. Well, not simple harmonic oscillator, I guess discrete analog of the second difference, second derivative. Yeah. Anyway, the point is that was the operator seen previously at order 1. Now it's acting on the the y1 term rather than the y0 term, and it's going to equal all kinds of stuff on the right-hand side, which comes from y0, which turns out to be this, minus partial with respect to s of y0 and plus 1 comma s. That's one such term. Then there's also a term plus partial with respect to s, y0, and minus 1, comma s. So those differ in their n index, those first two terms. And a term that comes from the cubic nonlinearity that we had that had an epsilon in front of it, that's going to give us a minus 2 omega squared y0 cubed evaluated at n comma s. So those are all the objects that come up at order epsilon that depend on the y0. And those are the terms that could potentially cause resonance. Some of them will, and some of them won't. So we have to expand the right-hand side. That is, we have to expand all this stuff by plugging in what we just solved for y0. So our strategy then at this point is now expand the right-hand side. And look for resonant terms. So resonant terms will be terms that are proportional to the solution of that linear difference operator, the homogeneous problem for it. So there'll be terms that are proportional to cosine alpha n plus theta and sine alpha n plus theta. That is, we want to read off the coefficients of those terms. It's totally analogous to looking for terms proportional to sine of omega t, or like sine t and cosine t that we saw in earlier problems in continuous time. So there is that same whole theory about resonant terms for linear difference equations. I don't have time right now to develop it, but we could do all of that if we wanted. So anyway, I'm going to expand the right-hand side and look for such terms, and then I'm going to try to eliminate them by choosing the coefficients in such a way that will eliminate these secular producing terms. Now, this is a bit of an annoying calculation to do by hand. So especially because of the cubing and, I've got to deal with these different subscripts, the n-1, the n+1. So you could do it. It's not that tough. I mean, it'll just take a minute or two. But since I'm doing it in real time, let me jump out and go to Mathematica and have it do it. And then I'll come back. So let's share the desktop. I did this morning. Here it is. Had a little trouble with some aspects of it. So is that visible enough? You want it any bigger? I don't know. That's always a question. I'm going to make it a little bigger. Let's see how bad it looks. If I go to 300%, okay. So I'm just going to write down my y0 of n comma s. There it is, a of s cosine alpha n plus theta s. Now, to look for the resonant terms, I'll write down the right-hand side of the order epsilon equation and just call it RHS. So it's what I just said, this derivative with this subscript at n+1, the opposite sign on this derivative, subscript at n-1, and then subtracting this 2 omega squared y0 cubed term. Okay, so I substitute in this y0, I get a bunch of junk. There it is. And at this point, Mathematica is giving me, first of all, a cosine cubed term, which I don't like. I don't want cosine cubed. I want to expand cosine cubed of something in terms of cosine of the argument and cosine of 3 times the argument. Because the cosine of the argument is what would cause resonance, and the cosine of 3 times the argument doesn't. So I want to expand it like that. I also want to expand all these other cosines in that way to isolate just the resonant terms. Meanwhile, you see I've got various derivatives, a prime of s happening, theta prime of s. So that's all good. Those are going to give me my slow time evolution equations for a and theta. All right, so anyway, I want to rewrite this trigonometric mess to get rid of the powers and products. I just want Fourier harmonics because I'm trying to just pull out, as I said, the coefficients of cosine alpha n plus theta and sine alpha n plus theta. So I asked Mathematica to do this by trig reducing the right-hand side, and it did pretty well. Gave me this cosine n alpha plus theta. I like that. Here's cosine 3n alpha plus 3 theta. That's good. But this term is annoying to me. I don't want an n minus 1 alpha. I want it to be smart enough, or actually I ought to be smart enough. I'm not very good at using this software. I wanted to know to do cosine of the argument n alpha plus theta, and then also split out a cosine of -1 times alpha using the correct, there's just a certain trig addition formula that would be helpful. And it doesn't, trig reduce is too blunt an instrument. It doesn't give me what I want. So I tried other things. Like I say, these trig terms with these terms in there are causing grief. So to finesse it, I just got rid of those. I'm showing this in case you're as bad at Mathematica as I am. This is how you can work around it. I defined a new phase to be the quantity that I like, n alpha plus theta. So I call that phi. And to enforce this, I replaced it theta everywhere by phi of s is mine, or by phi s minus n alpha. So anyway, I substitute into that previous expression. I got this thing, simplified it, and now it's looking pretty good. This is what I would have done by hand. I mean, this is the human way of simplifying the equation, except it still has simplify now gave me the cosine cubed back, and I don't want that. So I'm not going to trig reduce the whole thing, just the cosine cubed. So I wrote the right-hand side again, except trig reduced just the cosine cubed. And finally, it gave me what I wanted, which I probably could have done in one step if I were better at this. But anyway, it gave me this. And now it's cool, because now it's just cosine of this argument, sine of this argument. There's the occasional non-resonant term like cosine of 3 times the argument. I don't care. So I read off the coefficients of the resonant terms. Here's coefficient of the cosine term. That's this. The sine alpha is just a constant. Here's the coefficient of the sine term. I want to set both of those to 0 to eliminate secular terms. So I solve for what's the condition on the amplitude and the phase to make those coefficients be 0, and here they are. So these are my slow time evolution equations, which I will now write down back in. By the way, cosecant I'm going to write as 1 over sine. I don't really like cosecant so much. So let me share my iPad again. Okay. All right. So with that little assist from Mathematica, the slow time equations so the slow time equations from Mathematica were, it's interesting that we're actually getting differential equations at this point. That's because of that Taylor expansion that we did earlier. We're getting theta prime of s is 3/4. This is the one that had the cosecant in it. Omega squared a squared, and rather than write cosecant, I'll just divide by sine alpha. So there's that. And the other one, so this came from here. So prime means DDS. And the other one is much simpler. It's just A prime is equal to 0. Which is interesting and also very akin to what we saw in the Duffing equation, where because the Duffing oscillator was energy conserving, it kept a constant amplitude. Whatever its initial amplitude was, it just stays at that amplitude to lowest order. Its frequency changes, but its amplitude doesn't. So that's happening here too. Amplitude is just going to be constant on the slow time scale. Constant. And so then I can substitute that in for theta prime. And you see that theta prime is itself constant, 3/4 omega squared A0 squared all over sine alpha. So that's pretty easy to integrate because that whole expression is constant. So theta prime is just that thing times S. Or sorry, theta of S is just 3/4 omega squared A0 squared over sine alpha times S. And then I could put in, if I want, plus theta 0, an arbitrary constant like that. So that's it. Those are my solutions for what's happening at this long time scale. Pretty nice. And so notice what's happening. Theta, a phase, is increasing in proportion to S. That means this, if phase is changing linearly in time, that's like a frequency shift. So we're getting the same kind of phenomena that we had in continuous time. So putting everything together, well, actually, why don't I rewrite sine alpha? Because I earlier had, recall, what was it? We had a formula for cosine of alpha. Wasn't it cosine of alpha was, that was the thing we called B, which was 1 minus omega squared. So that would tell me that sine of alpha would be square root of 1 minus cosine squared of alpha. So that should be, well, whatever. Square root of 1 minus omega squared all squared, which when you simplify it gives omega times square root of 2 minus omega squared. Okay, so I kind of like that. I could clean up the whole thing. Let's see. So theta of S, which is what I'm interested in, is 3/4. Let's see here. Omega squared A0 squared over what I just calculated. Omega square root 2 minus omega squared. That whole thing times S plus theta 0. And I might as well cancel out 1 factor of omega. So let me do that. Do that manually like this. There, so that's a nice expression for theta of S. And actually, since I don't feel like writing all those constants over and over again, let me just call it gamma s plus theta 0, where gamma is this 3/4. So gamma depends on amplitude. And I think I've done that right. Yeah. Sorry for the ding. Better turn off my phone for a second. Okay, so I'm slowing down to a halt here. What's going on? So now what if we replace the S by, let's go back to original time. So this you could think of as gamma epsilon n plus theta 0. And excuse me, I'm sort of flustered about my computer dinging at me. Do not disturb, please. Okay. All right, so there. This whole thing is going to represent an order epsilon frequency shift. All right, and so I think that's pretty much all I wanted to say, right? I mean, I've got the theta of S. So what else is there to do? I mean, we've solved for both A and theta. So we have the complete behavior right here. And, you know, I mean, if you wanted to write that out a little more explicitly, I guess at this point we could say, you know, this expression above is asymptotic to our A0 cosine alpha n plus epsilon gamma n plus the theta 0 that we just calculated. So as you can see, what's happening is if this alpha, you know, represented a frequency, it's now gotten perturbed by this epsilon gamma correction. So I suppose what remains to be done is to test this against numerical solution of the equation. I didn't do that. I didn't get to that this morning, sorry. So I'm sure it works magnificently, as multiple scales often does. Maybe I'll leave that as an exercise for the reader or the viewer. Try it out yourself. It should really work like a charm, at least up to times of order, you know, 1 over epsilon. Discrete times of order 1 over epsilon should be excellent. And after that, it might start to break down. Okay, so I think that's all I'm going to say for today. Do you want to ask any questions at this point?
So since we have an epsilon dependency in the y0 term, then in order to be complete with the like epsilon to the first approximation, don't we need y1 as well? Because
Well,
we won't, sorry.
You go ahead, please.
I was saying you want to say that y is approximately y0 plus order epsilon squared, but y1 can also be order epsilon, right?
Well, you're right. This thing that I've written down is the order 1 solution to the problem that includes this order epsilon frequency shift. And so, but you're right, there's a term epsilon y1, which will cause order epsilon additive corrections to the answer. But I tend not to care about that epsilon y1 term that much, because although it makes this small additive change to the answer, it doesn't, I mean, because we've eliminated the secular terms, the epsilon y1 is a bounded term. It's uniformly of order epsilon over the time scale of interest. So we kind of captured the main qualitative behavior all here at order 1, just in the form of this frequency shift. But you're right, if you wanted an order epsilon accurate thing, then you'd have to calculate y1 itself. I don't know if you see the distinction I'm trying to make.
Yeah. So the solution we have here is just order 1 and not order epsilon, even though
That's
it has
right.
epsilon in it.
Yeah, so you could check
Okay.
that. I mean, if you do it numerically and subtract the full solution from this approximation, I think we would find that the error is order epsilon. But it will stay, the point is, it's truly order epsilon. It's not order epsilon times a secular term. It's just a bounded thing of order epsilon on the time scale up to order 1 over epsilon, and then at much longer times it'll start messing up at times of order 1 over epsilon squared. So anyway, yeah. Good. Other questions?
For the order 1 equation, when we were trying to look for the value of lambda earlier,
Oh, yeah.
is there any relation between that and how you would do a stability analysis for linear discrete time systems?
I think it's pretty much the same thing.
So if, okay, so then if we're saying that lambda in magnitude is 1,
Yeah.
then the stability analysis would be inconclusive.
Because you're saying we're getting pure imaginary.
Right.
I mean, because we're getting a pure imaginary exponent here. And so we're getting something that's exactly on the unit circle. So the linear stability analysis is not telling us whether, I mean, so you're referring to problems where you've done a stability analysis of the origin, right? So, or of a fixed point, of an equilibrium point. Yeah. And so that's right. When you find eigenvalues exactly on the unit circle for discrete time, map, that is inconclusive. The linear theory isn't telling you whether perturbations are growing or decaying. You only know that they're neutral at linear order, but you would need higher order information to decide on stability. So in this problem, we had a similar issue with the Duffing oscillator in continuous time, where we were getting simple harmonic oscillator closed orbits. I mean, what I'm trying to say is, if we did an eigenvalue calculation there, we would have gotten pure imaginary, which would be similarly inconclusive. But we could use a conservation of energy argument, which is effectively a nonlinear argument, to show that the orbits for Duffing's equation stay, first of all, they're closed and they stay bounded. So it's an interesting question. Is there an analogous nonlinear argument here in this discrete equation? I mean, we're predicting periodic solutions for small epsilon. What's the real story? Does this thing have periodic solutions? Or does it have just only very slowly growing or decaying things that are nearly periodic, but not really? I don't actually know the answer to that. That's sort of related to Mark's earlier question about delta t. That this would be, for those of you who've taken numerical analysis, this would be like asking, if I solve Duffing's equation with the Euler method, right, which is the crudest numerical integration scheme. And you just, basically what we did here is Euler's method, discretization. That's what this is, where you replace a first derivative by its discrete difference. If you just do that thing, what will Euler's method show you? Will the solution stay bounded and periodic or not? In my experience, Euler's method will produce unstable spirals for systems that have closed orbits. So I bet if we solved this difference equation in the computer, we would see slowly growing oscillations. That would be, and I don't know if that's qualitatively, that seems probably right. I think that's probably what the real behavior is for the difference equation. I don't know, I'm making this up, I'm guessing. But that's interesting. I mean, it's really a very interesting issue to compare differential equations to difference equations and look for sorry to keep saying differences, but look for differences between them, compare them. Yeah.
But
That's an
also
interesting,
this,
go ahead.
so this linearity in the first order was, I guess, a byproduct of this method we use. We tend to see those linear equations when we do
Right.
perturbation methods at each order.
That's
So
right.
if you were to do any kind of fixed point analysis on a order one equation, I guess you can't necessarily be certain that any results you get from that are true about the exact equation, can you?
Well, because you're saying the linear operators that we use often have neutral stability. They often have inconclusive eigenvalues.
Right.
Yeah, that's often true. Yeah, I mean, it's because culturally, this field has grown up doing small perturbations of neutrally stable systems like harmonic oscillators. Yeah, and that's, you know why? It's because if you don't do systems like that, the weak nonlinear terms can't make a difference. If you have something that has a linear stable solution, adding a weak nonlinearity doesn't change anything. The only place where a weak nonlinearity can have an effect is if the system was neutral to begin with. Then the small nonlinear terms can accumulate over long time scales. Their effects can accumulate. So it's an interesting thing. I mean, the philosophy is, I want to do perturbation theory to understand the effect of small forces. The only place where perturbation theory is interesting is when small forces can make a long-term difference. And so because of that, I'm only going to study things that are kind of very degenerate and neutral. At least that's what's happening in this part of the perturbation theory universe. These statements I made are not really true for WKB or boundary layer, but for multiple scales and Poincaré-Lindstedt, it's mostly about weakly nonlinear systems. So yeah, so you asked, would that mean that at the conclusions we might make at the linear order, that we can't make conclusions? That's right. Yeah. That's why you're doing nonlinear analysis in the form of perturbation theory. Yeah. Okay. All right. So let's see. Next time, I don't know what I'm going to do. It might be something with perturbation theory for partial differential equations. And I don't know if I'm going to try to do it with renormalization techniques or just some more conventional old-fashioned technique. I don't know, but we'll see. I'll figure it out before next lecture. Okay, see you then.